Okay, so this is P6. We're going to be looking at radioactivity in this lesson. So, first of all, we're going to start off with the structure of the atom. It basically is made up of positive protons and neutral neutrons. Their masses are pretty much the same, and then we've got some negative electrons around that central nucleus. Okay, pretty much there's a lot of empty space in the atom, and we've got these tiny electrons which are approximately 1700 times smaller than protons and the neutrons. Okay, you should know for your exam that a nucleus is approximately 10 to the minus 15 meters wide, and that an atom is 10 to the minus 10 meters wide. Okay, and gives you a rough idea that small molecules as well are about 10 to the minus 8 meters wide. Okay. Right, the next thing you need to be aware of is what we call the nucleon number, or the mass number, which is the larger of the two numbers that you see next to the element's symbol, and then the smaller number, which is the atomic number or the proton number. Okay, so the smaller number is obviously the number of protons in that particular atom. 13 is obviously going to be the number of neutrons plus protons, so the amount of nucleons. So that's what I've just told you. Then also the number of electrons is also going to be the smaller number, the atomic number as well. Okay. Other thing you need to be aware of is what an isotope is. So this definition is basically an element, okay, that's got the same number of protons in the nucleus but a different number of neutrons. Okay, so that's what the definition of an isotope is. Okay, so this table, you can pause the video. Basically, you should know the relative charges and relative masses. Okay, protons are going to be +1, electrons are going to be -1, and then positrons, which are positive electrons, the antimatter of electrons is also going to be +1. Okay, but bear in mind the mass of a positron is going to be exactly the same as the mass for an electron. Okay, so I told you roughly an electron's mass is approximately 1700 to 2000 times more smaller than a proton or a neutron. Right, so you need to be aware of that all atoms are neutral because they have the same number of positive protons and negative electrons inside them. Okay, they only become positive or negative when they lose or gain electrons, and then we call them positive or negative ions. Okay, so make sure you are aware of what ions are and don't get them confused with isotopes. Right, electrons are also set at set energy levels, which are a set distance from the nucleus. The ones that are the most stable will be the ones closest to the nucleus because they're closer to the positive charge, which they're attracted to from the protons, and the electrons on the outer shells are most likely to leave the atom just because they're further away. Okay, and we've talked about this point here. If you've got some EM radiation, okay, being put into the atom, electrons can be excited, they can move to a higher energy level, and when they drop down, the same type of EM radiation gets emitted, okay? Right, so remember our title is radioactivity. So what is radioactivity? Well, basically, radioactivity is when unstable nuclei, really heavy nuclei, okay, basically decay, and they emit several forms of radioactive particles, which we will look at later on. Okay, but remember, it is a random process. Okay, there's no way of predicting what type of radioactive particles will be emitted. Okay, so we'll look at that in a second. Right, but what does ionizing radiation do to atoms? Okay, well, if we know what an ion is basically an atom that has lost or gained electrons. Essentially, it means that ionizing radiation will do this to atoms, okay? And we'll look at that in more detail in a second. What is background radiation? Well, background radiation is all around us, okay? If we look at this graph here, okay, majority of the background radiation comes from radon gas, okay? We've got radiation just coming from general living things, okay, a very small amount coming, believe it or not, from nuclear power plants. We've got some coming from cosmic rays, and then we've got some from rocks and buildings, because we've got heavy elements in them generally. And then obviously we've got X-rays, gamma rays from medical equipment, okay, used in hospitals. So how can we measure the amount of background radiation? Well, we use a device called a Geiger Counter or Geiger-Müller tube. Okay, so basically it records the amount of radioactive particles hitting the inside. Sometimes we can use a photographic film as well, and essentially in the same way that light develops photographic film, the ionizing radiation does the same as well. Okay, so if it was originally black, where the radioactive particles would hit the film, it would turn white. Okay. So let's look at these radioactive particles. What are they? So an alpha particle is essentially 2 protons and 2 neutrons, or a helium nucleus, okay? 2 protons means it's got a +2 charge, and it's quite heavy, relatively, okay, to these other particles here. A beta particle is an electron, okay? There's also a beta plus particle, which we'll look in a second, okay? But obviously they're much more lighter than an alpha particle, and they're either got a minus charge if it's a beta minus particle, or a plus charge if it's a beta plus particle. Last form of radiation is essentially a gamma ray. Okay, remember a gamma ray is essentially part of the EM spectrum. Okay, it's the highest frequency wave of the EM spectrum. Right, let's look at some of the properties of these particles. So alpha particles can be stopped by paper or skin and has a range of approximately a couple of centimeters, 3 to 5 centimeters in air. Okay, it's worth remembering this in exams because they tend to ask you some of the properties and what each particular particle can be stopped by. Okay, so beta particles can be stopped by aluminium, has a range of approximately 1 meter in air. Gamma rays are reduced, okay, by lead or concrete and has a range of about 15 meters in air. Okay, they generally do have a very long range, but generally in 15 meters you'll be heavily exposed to gamma, okay, and that'll be quite dangerous for you. Right, the most ionizing type of radiation is obviously going to be alpha particles because they're +2 charges. Least ionizing is going to be gamma because they're neutrally charged. Okay, so if you've got an alpha particle next to one of your skin cells, atoms in your skin cells, the 2+ charges are going to attract your negative electrons from your atoms, which will cause your cells, your atoms in your cells to obviously malfunction because they'll be unstable, and therefore that's how tumors can form. Okay, from cells not functioning properly. So let's have a look at how the model of the atom developed. Okay, so what we originally thought of was that it was sort of like a plum pudding model. Okay, so basically we thought of it as dough, okay, with a positive charge, and then negative charges randomly were arranged throughout the dough. Okay, so if you think about a sort of like a Christmas pudding, that would be your positive charge, and then your raisins and fruit would be the negative charges, just randomly arranged. Okay. Now, in order to test the plum pudding model of the atom, Rutherford, okay, this was in Manchester, carried out an alpha particle scattering experiment using the equipment to the left here. Okay, alpha particles from this alpha source were fired at a thin piece of gold foil. Where the alpha particles were detected was recorded before repeating the experiment. So essentially this alpha particle detector, okay, was moved around, okay, this gold foil 360 degrees, and the amount of alpha particles detected was recorded. Okay, he made these following conclusions. Okay, he said that the atom is mostly empty space because most of the alpha particles went straight through. The nucleus contains most of the mass because it could deflect fast alpha particles, and the nucleus is positive because it could deflect positive alpha particles. And he said electrons orbit the nucleus because all atoms are neutral. Okay, so instead of the plum pudding model, in order for the alpha particles to be deflected by large angles like this, okay, he said that there would have had the positive charge had to be concentrated at a central point, okay, which he thought would be the nucleus, the center of the atom. It's the only way to explain why the alpha particles deflected at such a large angle. Okay, and it had to be positive because positive charges repel each other. Okay, and we know the atom is mostly empty space because most of them literally went through. Okay, so we had a high percentage of alpha particles being detected here. Right, so Niels Bohr developed this model slightly further, and instead of stating that electrons orbited the nucleus like the Earth orbits the Sun, because that would mean it losing energy as it spiraled into the nucleus, okay, he stated that electrons could only exist in discrete energy levels which were a set distance from the nucleus. Okay, it meant that electrons could not exist in between those energy levels. And until this day, okay, physicists still follow this model. Okay, it fits the data that we observe when we do experiments with atoms. Right, now let's look at beta minus decay. So in beta minus decay, okay, a neutron becomes a proton and an electron. Okay, so this is a very important point that you've got to remember for your exams. Okay, so if I look down here, so beta minus decay is this one here. Okay, so we've got our original element, okay, with its mass number and atomic number, okay, which will then decay into another element where its mass number and proton number will change, and we've emitted a beta minus particle. Okay, so essentially we're going to have one more proton here because a neutron is becoming a proton, but our mass number will stay the same. Okay, and the way to remember this is if you do simple maths, let's say you had Z was 10, okay, this would have to be 11 because 11 minus 1 has to equal 10. And let's say A was 20, your 20 would still remain the same because we've still got the same, well, we've got the same total number of protons and neutrons. Okay, the only thing that's changed is one neutron has become a proton in the nucleus. Okay, this is due to the weak force. Okay, so something weird happens in the nucleus to cause this change to occur. Right, in beta plus decay, the opposite happens. So a proton becomes a neutron. Okay, so beta plus decay is this one here. Okay, so this time, let's say we've got 10 here. Okay, this time this is going to be 9, okay, because we've got a proton becoming a neutron. So 9 plus 1 will give us 10. And again, we've got 20 there and 20 there. Okay, so just bear in mind when you have beta plus decay, just ensure that this number plus that number plus 1 has to equal whatever the original number in the atomic number here was. Okay, we've also got alpha decay here, which essentially is this symbol here. So we were losing 2 protons and 2 neutrons as well, because this 4 signifies 2 protons and 2 neutrons, which means, let's say this was, I don't know, this was 100, let's say A was 100, the top number here would be 96, so 96 plus 4 has to equal 100, and then let's say this was, I don't know, 50, this number here would have to be 48, 48 plus 2 equals 50. So we're now going to look at neutron decay. Okay, so remember, neutrons are essentially a nucleon. Okay, so they're part of the nucleus, and technically you could say it is one form of radioactive decay, and it's just due to sometimes heavy nuclei having too many neutrons, and basically due to their instability they emit one neutron. The important thing to note down here, the atomic number is 0 and then our mass number is 1. Okay, so same principle applies. Let's say we've got 100 here, this has got to be 99, so 99 plus 1 equals 100. If this was 50, 50 would be the Z, and then we'd have 50 here because 50 plus 0 equals 50. Okay, with gamma decay, so this is going to be the symbol for gamma. Okay, notice there are no protons and no neutrons in a gamma wave, so essentially it's just excess energy. So we've got literally no change to the nucleus, to the internal structure of the atom whatsoever. So this number could be 100 and it will be 100 here, that could be 50 and it will still be 50 here. Okay, so please pause this video, just make sure you are familiar with these radioactive decay equations. It's very common for examiners to ask you to fill in one of these numbers. Okay, could be either one of these numbers here, either one of these numbers here, or even get you to identify what particle, what number goes in your respective radioactive particles. So please make sure you've got this. Right. After a nucleus has gone through radioactive decay, it often gives off excess energy as gamma. Okay, that's what I told you. Please bear in mind, no protons or neutrons leave it. Okay.